All right, the next example involving non-negative random variable and showing us an example of the hazard function is going to be going to derive a new distribution, which is called the Rayleigh distribution. Okay. So what is the Rayleigh distribution? So let's now suppose that we have a random variable t, which has the hazard function that is linear in t. So lambda of t equals t. Then based on what we've done up above, we can immediately derive the density and the survival function. Okay, the survival function of t is exponential minus integral 0 to t of the hazard function, which is just s ds. That integral is going to be e to the minus t squared over 2. And the density of t is the hazard function times the survival function. So it's t e to the minus t squared over 2. So what is a random variable like this? How does it behave? And in particular, so what we see is that this is a case where you have an increasing force of mortality. This is not a memoryless distribution, right? If you've lived 100 years, you're 100 times more likely to fail in the next instant as something that's been around for 1 year, for example. So that makes a lot of sense. This is a variable that has aging. There are variables that have anti-aging that get a bit stronger as they go. Okay. So expectation is t e to the minus t squared over 2 dt. We have to do a little bit of manipulation here. But if we do that, we end up with, okay, so how are we going to do this? Well, let's notice that this is t squared, e to the minus t squared over 2. So that's a symmetric function. So that's an even function, right? So that's going to be at -2, it's the same value as at +2 because it only comes through in terms of t squared. Okay. So this is 1/2 then of the value if I were to integrate this from -infinity to infinity of the same thing. But now when I do that, what am I doing? Well, I'm actually looking at something that's kind of like the second moment of a normal distribution. Normal distribution, a standard normal distribution. So in order to do that though, I have to put the square root of 2 pi in the denominator, and so I have to put it in the top. And now I have this here, which is the expectation second moment of a standard normal, which is 1. Calculated that before. And so what I'm left with is square root of 2 pi divided by 2, which is same as square root of pi over 2. Another way to do this would be to integrate the survival function. So for non-negative random variables, remember we can compute the expectation by integrating the survival function over all possible values. The survival function in this case is e to the minus t squared over 2 dt. Okay. Can do the same thing because the thing on the inside, again, looks just like the density of a normal 0, 1, except it didn't have its normalizing constant. If we put the normalizing constant in, then we have an integral from 0 to infinity of the normal 0, 1 density. This is the probability that a standard normal is bigger than 0, which is equal to 1/2. So this is square root of 2 pi over 2, which again is square root of pi over 2. Okay. For the variance, we also have expectation of t squared. We've seen before how this can be computed as 2t times the survival function dt. Which is integral t e to the minus t squared over 2 dt. But that's the expectation okay. And we see that this is equal to, if we work this out, which we can do integration by parts, and we've done this in the past, in the Gaussian case, then we'll see that this is equal to 2. And then the variance of t is equal to expectation of t squared minus the square of the expectation. So this is 2 minus pi over 2. In this example, t said to have the standard Rayleigh distribution. So this was what we defined in terms of having the linear hazard function, and we worked out properties from there.